So welcome back to the second week of our summer school. This week's topic is Boolean functions. We have the pleasure to have one of the leading experts on this topic, Professor Yuval Filmus, to tell us everything about it.
Thanks. So the plan for these 5 lectures will be a mix of some classical, if you can call them, starting in the 80s, so classical stuff and some newer stuff. For the classical stuff, I'll try to do everything in full, so you get a feeling for how things are done. And for the newer stuff, probably won't be possible because it's a bit too much. Okay, so what is Boolean function analysis? It's the study of functions f from plus minus 1 to the n to plus minus 1 from a spectral perspective. Okay, so I'm using plus minus 1 to the n because it's a bit more convenient for me, but sometimes you see 0, 1 to the n. We will also see 0, 1 to the n in the future. And then we'll see what this spectral perspective is in a moment, but where do these Boolean functions come from? So I think the first few works in this area were in social choice theory, so we will see some examples of that. So there's some voting going on, and there's some function which somehow describes the outcome of the vote. Okay, so this is the function f. Or in applications in theoretical computer science, and this f is a function that computes the output of a Boolean circuit, maybe. Or perhaps it's something having to do with error-correcting codes. Or maybe it's a graph property, especially something about calculation. So this is where these Boolean functions come from, and we want to know some structural information about them. And this Boolean function analysis is really a suite of tools developed to understand Boolean functions. Now, I said Boolean functions, there are 2 things here which are Boolean. So it's both the domain of the function and also the output. Okay, but sometimes we talk about real valued functions when we want to understand them. And sometimes instead of the Boolean cube, so this is known as the Boolean cube, instead of the Boolean cube, we are interested in a different domain. And all these things are still called Boolean function analysis. Okay, just for historical reasons. Okay, so our starting point will be the fundamental theorem of Boolean function analysis. The fundamental theorem of Boolean analysis. If you look it up on Google, then I'm not sure you'll find anything because it's a name I invented. So every function f from the Boolean cube plus minus 1 to the n to the reals, or if you want, you can work with the complex numbers, but I don't like them, so we do real values, as a unique representation f of x is the sum over subsets of the numbers 1 to n of some function, so some real number times this function, where this function ts is just the product of xi's for I and s. Okay, so this x is x1 up to xn. Okay, so what this is saying, that if you look at any function, not necessarily Boolean, but any real valued function, or in principle complex valued function, then you can present it as some linear combination of these functions that we call the Fourier characters. Or, yeah, basis functions. Okay, and sorry about the mess. So these numbers are known as Fourier coefficients. And this entire sum is called the Fourier expansion. Okay, so you can see that everything here is named Fourier this, Fourier that. And this is because this is just a special case of Fourier analysis. So this is a combinatorics crowd. So maybe you're not familiar with this general theory of Fourier series, whatever. I'm not. Okay, but for if you want to sound mathematically sophisticated, then there's this general notion of Fourier analysis on locally compact groups. And here the group is Z2 to the N. Okay, now that I've said it, you can forget about it. Yeah, because we're not going to use this abstract theory. And we're doing combinatorics, we like concrete things. Okay, so every function f can be written as some linear combination of these Fourier basis functions or Fourier characters. They're called Fourier characters because they're characters of the group that has any meaning to it. Okay, so the first thing we're going to do is we're going to prove this fundamental theorem. Okay, so there are many ways to prove it. It's not a difficult theorem. It's just the starting point of everything that we're doing. And we'll see that even just using this theorem, we can already do stuff which is really not so clear how to do it in any other way. Okay, so any ideas? Why is this thing true? This will be proof. Okay, so we will show that the functions Ts form an orthonormal basis with respect to the inner product f and g. So the expectation over x, the uniform distribution of f of x, g of x. Yeah, you don't need to prove it this way, but we will need this anyway, so that's why we're proving it this way. Okay, so these Fourier characters are form an orthonormal basis for the space of all functions from plus minus 1 to the n to the real numbers. Okay, so once we've seen that, okay, what does it mean for these functions to be orthonormal? So any two different ones, they need to be orthogonal. So the inner product has to be 0. And if you take the inner product of a function with itself, then it needs to be to have norm 1. Okay, this is what it means to be orthonormal. Now it's a basis because there are 2 to the n Fourier characters, and 2 to the n is also the dimension of the space of all functions. Okay, so that's why it works. But you can really also show it in many other ways. I mean, it's an easy exercise. Like what this really means is that you can express every function here as a polynomial in the inputs. And this polynomial, it's enough for it to be multilinear. And the reason is that each coordinate is plus minus 1. So if you square it, you get 1. So it's pointless to use higher powers. Okay, so this is the low-tech way of saying it. But we will need this anyway, so we prove it this way. Okay, so first let's see that it's everything has norm 1. So every ES has norm 1. Okay, so I'm just using it so I can demonstrate to you the notation. So this will be the L2 norm. Okay, it's just the same as the inner product of the function with itself. Okay, and by definition, this is expected value of ES of x squared. But what is ES of x squared? It's not a trick question.
What?
The 1. Yeah. Okay, so this was easy. Later on, we will see the bias square basis, where instead of the uniform distribution over the cube, there will be some other distribution. And then this property will be maybe more exciting. But we will actually need to do something. Okay, and the second thing is if S is different from T, then TS and PT are orthogonal. Okay, so without loss of generality, there is some I which is in S and not in T. Okay, there could also be something which is in T and not in S, but it's the same. So let's just assume there's something in S and not in T. And now ES, ET, you can write it. Okay, so it's the expectation of X of ES of X, ET of X, okay, which is the expectation over just Xi, Xi, and the expectation times the expectation of the rest of ES minus I of X minus I, the T of X minus I. So we're abusing notation and whatever. And all this is saying is that if you just write these two products together, then Xi only appears once. So you can write Xi and then you can write the rest. Okay, and because everything is independent, then we can decompose this expectation into a product of expectations. Okay, this is all I'm saying. Okay, now the expected value of Xi is 0. And this, we don't care what it is, so this entire thing is 0. Okay, and maybe a different proof, which is what I was intending to show, but okay, a different idea, but very similar. So ES of X times ET of X is the S symmetric difference T of X. Okay, so when you multiply the things in S and you multiply it by the things in T, then the things in the intersection, they cancel because Xi squared is 1. So you get a symmetric difference. And now you have to show that if you take any character which is not the empty character, and you take expectation, then you get 0. And then the proof is like the same as here. So it's really the same proof, but maybe expressed slightly differently. Okay, so this nice property that the characters form a group. This only happens when you use the uniform distribution over the Boolean cube, and it won't happen when we switch to different distributions. So we'll have to remember it for the future. Okay, so this group property, it's actually what we're going to use in our application, but it's only, it's this one property which is somewhat less representative of what we actually need in this area. Okay, so this completes the proof of this fundamental theorem of Boolean function analysis. Yeah, it's easier than other fundamental theorems, maybe. Okay, what's really happening here is that we take this orthonormal basis for the one-dimensional Boolean cube, which just consists of the functions 1 and xi, and then we tensorize it. We take products to get the basis for the n-dimensional Boolean cube. Okay, that's what's happening behind the scenes, but you can just do everything explicitly, and then you don't need to be abstract. Okay, so now let's see some consequences, but first, are there any questions? Good. If you do have questions, I really recommend asking, because otherwise you will be lost and you won't understand anything. Okay?
Sorry,
Yeah.
do you mean that if the distribution for for x is not uniform again, then one or two will fail?
Yeah, so if the distribution is not uniform, and we'll actually see this, okay, so why is this interesting? So in the GNP model of random graphs, unless p is equal to half, then this is not the uniform distribution. Okay, and we will have to change the Fourier basis. Okay, we'll see it when we get there. But one thing which certainly won't be true is this sort of property. Okay, so here when you multiply two characters, you get a different character. And as it so happens, in the bias case, you multiply two characters, you get something, which is not a character. Okay, so this property, which is actually, we're going to use it right now when we discuss linearity testing, is a kind of property which happens sometimes, but it's not the typical case. Okay, so maybe it's a bit misleading. Any other questions?
I'm sorry about we don't know the definition of the Fourier coefficients.
Yeah, so the definition for the Fourier coefficient, we'll give a formula in a moment. It's just, so this theorem states that there is a unique representation of every function f as this linear combination. And the Fourier coefficient corresponding to s is the coefficient of s in this unique linear combination. Okay, so you represent this function f in this basis, and the coefficients are called Fourier coefficients. If you represented instead this function f in the spatial basis, so like the delta functions, then the coefficients are just the values of the function at all the points. And here we switch basis. The basis switch matrix is the Adama matrix, if this helps. Okay, so if you do it twice, then you get back to the original. We're not going to use it, but it's true. Yeah, but we'll give a formula for the Fourier characters in a moment. Any more questions? Okay, so as a consequence, see some basic observations. And they're all more or less going to follow from the Fourier characters forming orthonormal basis. Okay, so the first thing is a formula for the Fourier coefficients. Okay, so this is the inner product with the corresponding Fourier character. Yeah, and like I can prove it, but this is really, you learned it in linear algebra. So it's just an orthonormal basis. So if you take an inner product with one of the basis elements, then you get the coefficient. Okay, the way to prove it is to open this thing up into a sum, and the inner product is linear. And okay, but I'm not going to show it because we'll see something similar. And anyway, you're supposed to know this. So if you don't know this, it's okay. Maybe you don't remember, but you can just refresh yourselves later. Okay, so this is the formula for the Fourier coefficient, and this is another way of seeing that this expansion is unique, because we have a formula for the coefficient. Okay, now we have our Sabaz identity. Yes, it also that's true for any orthonormal basis. So if you take the inner product of two functions, then you get a sum of the product of the Fourier coefficients. Okay, and like we never do it, but in principle, you could define an inner product on the Fourier side, which is just defined like this, where the inner product of two Fourier expansions is just you sum everything. Okay, and you see there's a difference in normalization. Here we take an expectation, and here we take a sum. Okay, I think when people do continuous Fourier analysis, like in if you're electrical engineers, then they sometimes don't like this. So sometimes they use a different normalization, like maybe they move the expectation here, or maybe they split it half-half so that both sides have the same normalization. We always use this normalization. Okay, so this is Parseval identity, and a special case is this thing, which is a very useful property. So if you take the sum of the squares of the Fourier coefficients, then you get the alpha norm squared, which is also just the expectation of f squared. Then, in particular, if f is plus minus 1 valued, then this will just be 1. And if f is 0, 1 valued, then this will be the same as the expectation of f. Okay, so these are the two common scenarios. Okay, so both of these things are called Parseval's identity. And again, this is really just linear algebra. Okay, so to prove this, you write a double sum and it just works out. But this is true for every orthonormal basis. Okay, and a similar property. So what's existing?
One.
Okay, it's not always 1. Let's take f is a 0 function, then this will be 0. So it can't always be 1.
Expectation of f.
Expectation of f. Okay, and why is it the expectation of f?
That's the inner product of f, but with the empty function.
Right. So this is because empty is the 1. Okay, and now we use this formula. Okay, so we're actually, I don't think we're going to see any applications to external combinatorics, although it's possible to prove the Erdős-Collatto theorem this way. When you don't get anything doing it, but you could. You'll have to do this bias square analysis because the Erdős-Collatto is kind of boring for people's help. But if you did prove the p-biased version of the Erdős-Collatto theorem, then you would use these two properties, and everything will be 0, 1 valued, and yeah, it will be a very complicated proof of the Erdős-Collatto theorem. But you'll be able to prove stability very easily. But I don't think we're going to see this unless we have like a ton of time. Okay, so these are some basic observations, and the only thing here which is not true for any orthonormal basis is this property. Okay, questions? So now we have enough background and we can see an actual application. Okay, so like it's not even half an hour and we can already do something interesting with this. Okay, so we're going to see this classical analysis of linearity testing. Now, if I were doing this in a class, then I might spend a bit more time to see the original analysis, which involves something called the magic square. Okay, just to pick your interest, magic square. But here we're concentrating on Boolean functions, so you won't see the magic square, you'll see the easier proof using Fourier analysis. Okay, so I haven't yet told you what this linear testing is, so let's do it now. Okay, to explain where the name comes from, then we'll temporarily switch back to 0, 1. Okay, so in applications to experimental combinatorics, actually we usually do 0, 1. And when we move to this bias square analysis, we'll also switch to 0, 1. But for now, we stick to ±1 because it's a bit less cumbersome. Okay, and it's also good for you to be able to move from one to the other. Okay, but for the moment, let's switch to 0, 1. So the definition, the function f from 0, 1 to the n to 0, 1 is linear if for all x and y in 0, 1 to the n, f of x plus y. So this means you XOR, if you sum out to all the coordinates, equal to f of x plus f of y. So really you should think of 0, 1 here as Z2, and then this is just the addition in the group Z2 to the n. This is addition in the group Z2. That is the correct way of thinking about it. Okay, so a function is linear. This is just the linear algebra definition of linear. Okay, it's not something very exciting. Okay, so which functions are linear? Like if I wanted to do a list of all the functions which are linear, how do they all look like? Just so we understand the definition. Okay, what's an example of a linear function? Xi, right? So let's do examples. Okay, the other examples? Okay, sum of
Linear.
now we can take any sum of size. Or we can take 0, it's a special case, it's also a special case. So as a theorem, which you all learned in linear algebra, f is linear if and only if there exists a set S such that f of x is the sum of xi for I in S. Okay, and the way that you prove it is you look at the base elements. So what f does to like EI, E1 to EN, and it just works out. So this is just a linear combination with arbitrary coefficients, and because everything is 0, 1, then we can write it this way. Okay, I can do it slightly more slowly. So from linear algebra, we know that linear functions are inner products with a constant vector, and this constant vector is 0, 1. So if we just take the ones, then we get this expression. And we're also going to see a proof of this using Fourier analysis. Okay, so this was 0, 1. Now we're going to switch from 0, 1 to ±1. It's just for convenience. You can do everything in the language of 0, 1, but so if you switch to ±1 to the n, so the way you convert from 0, 1 to ±1, you take -1 to the power of. Yeah, so 0 goes to 1 and 1 goes to -1. And then XOR corresponds to product. Okay, so then this property is f of xy is equal to f of x, f of y, where this xy, this funny product, is just is the Kronecker product. You multiply the elements. Okay, and then this is just TS. the Fourier character. Okay, so these are all the linear functions. Okay, so you can check that if you take one of these characters, then it satisfies this property. Okay, it's quite easy from the definition. So I don't know if it's, yeah, it is on the board. So if you take the product of I over S of xi, yi, this is the same as taking the product of just the xi's times the product of just the yi's. Okay, so far, so good. And now to make it more interesting, guess maybe we'll keep this for now. It has all the basic definitions. So now what we're going to do, we're going to ask, this is the question. What can we say about function f from plus minus 1 to the n to plus minus 1 if when you take x and y random, then the linearity property holds with probability at exactly 1 minus epsilon. Okay, so if this holds with probability 1, then the function is linear. Now let's say that x and y are chosen uniformly at random, and this property holds with probability 99%. Okay, what can we say about f? What does f look like? And so this is the kind of question that we ask in Boolean function analysis. And for the answer, we want some answer where the error parameters don't depend on n. Okay, we'll see it in a moment, but this is part of the goal of Boolean function analysis, to get results which are dimension independent. Yeah, but we'll get to it soon. Yeah, so what can we say about f if the function is almost linear in this sense? Okay, in the sense that this linearity property, it holds with probability close to 1. Okay, why is this question interesting? So this is an almost homomorphism, and this is interesting for people doing groups. So it's a natural property, you know, in combinatorics, you can ask a ton of natural questions, and this is an example. Some of these questions are more interesting, especially if English asks them. And there is a connection to property testing, which I will explain later. There's also a connection to hardness of approximation. Yeah, has anybody heard of hardness of approximation? So I'll also spend a few minutes on this later, because this is really where Boolean function analysis mostly, well, not exclusively, but this is where all the hard stuff is being done in TCS with regard to Boolean function analysis. So it makes sense to mention it. We'll get to it later. But I think it's a reasonable question if you don't know all the different applications, like where it came from. But this is not something arbitrary. Okay, so the first paper mentioning it was there's something about self-testing programs, self-correcting programs, something about what if your program is, how can you test if your program works correctly? What if it works correctly, but only on most inputs? Can you then somehow get a program which works for all inputs? I think this was the original motivation. Since then, people forgot about that particular motivation, and now they have different motivations. Yeah, so what can we say about f which satisfies this property? What do you think? What would you like to be true? So can you give me an example of function f satisfying this property?
It looks similar to a linear function.
Right, so you would expect that f is similar to a linear function. So for example, if you took a linear function, so a Fourier character, one of these functions, then it will satisfy this property. Now let's say that I took a linear function and I changed epsilon over 3 of the entries. right? And epsilon over 3 fraction of the entry. Then this will still hold. Yeah, and I think you can improve this epsilon over 3 to something slightly higher. Okay, so the guess will be, I hope, f is close. We'll see how close to Fourier character or some x. Okay, and it turns out that this is the case. So the theorem if f satisfies property, then there exists a character S such that the probability that f is equal to Ps is at least 1 minus epsilon. Okay, so in this case, it's true. And you should think about these things like the stability version of L-Colorado. So in L-Colorado, this is the external combinatorics group, so I'm sure everybody knows this. But if not, then you can look it up later because it's very basic in your area. So let's do the p-biased version. Maybe you're less familiar with that. So now, usually the L-Colorado theorem is stated for sets of size k. And now instead, the set can be whatever, but we look at the biased measure, where the bias is k over n. Okay, so otherwise it's the same. So in the p-bias setting, the L-Colorado theorem states that when p is less than a half, then the maximal measure is mu p measure is p. And if a set has measure exactly p, then it has to be a dictator or star or whatever you want to call it. Now the stability version means that the only way in which the measure can be very close to p is if you're close to a star. Okay, so this is the same kind of stability version. And indeed, this particular statement about the L-Colorado theorem, it corresponds to a fundamental result in Boolean function analysis called the FKN theorem, Filmus theorem, which we're not going to discuss unless I'll go very fast and there will be tons of time. Yes, but this is another one of these results. So there's this 100% structure where if you're linear, then you have to be this character. And this is a 99% structure. So if you're almost satisfied with this linearity property, then you're close to a character. And this also implies a 51% or 1% result. So if you take epsilon, which is equal to half minus delta, then you get that if probability that f of xy equal to f of x of y, if this is larger than half plus delta, then there exists S such that the probability that f is equal to Ps is at least half plus delta. Okay, so what's going on here? So if you take f to be a random function, then the probability that f of xy is equal to f of x f of y will be very close to a half. Yeah, and this is because when you multiply two random xy, then you get another random element of the cube for this product distribution. Okay, so if you take f to be a random function, then this probability will be very, very close to a half. Okay, so this means that if this probability is bounded away from a half, let's say in this case it's more than a half, then the function cannot be random. It needs to have some kind of structure. And the structure that it has, it correlates with one of the characters. And this is called the list decoding regime. And this is what is actually used in this hardness approximation that I will discuss briefly later. Now, why is this called list decoding? So who here is familiar with list decoding in general? We don't have coding theories here. Error correcting codes. Are you familiar with error correcting codes? I'll take it for a yes. So in error correcting codes, there is this notion of unique decoding. So there's a code word and we add some noise, and you would like to say if the noise that we added is not too much, then I can get back the original code word. Yeah, this is unique decoding. But if I have too much noise, and this cannot possibly be true, or that there are these bounds that say that this cannot be done. But maybe I can get a small list of code words, short list, like sure, it could be constant or a polynomial or whatever. Yeah, this is called list decoding, and it's useful even if you're just interested in unique decoding, because maybe you can construct uniquely decodable codes from list decodable codes. Okay, this is called list decoding because this kind of statement can only be true for a few characters, yes. Okay, so it turns out that this is the same as, I think, the Fourier character being at least delta or 2 delta. We'll see in the proof, or maybe it's delta. And because of this property, then we know that this cannot be true for more than 1 over delta squared many characters. So kind of you can decode your function f to a short list of characters. And this is what is used in this harness of approximation that I'll get to near the end of class today. Okay, so yeah, this theorem, you can prove it using this magic square argument, which I'm not explaining to you, but it's very nice. So in short, how would you like to prove this kind of statement? So one way is you want to take this function f and you want to somehow reconstruct the character. Okay, so how would you reconstruct the character? So you can write this property in a different way. Okay, so this everything here is plus minus 1, so I can switch things around. Okay, and this means that if now let's say that you have this, so if this theorem is true, then this f is really this character hes plus some noise. Okay, and I want to get rid of the noise. So I want to know what is the real value at x before adding the noise. So I can look at this thing, A over all y, and I can take the majority value. It's called self-correction. So if f is indeed close to a character, then when I take the majority, then I should get the character if the noise is not too much. And it turns out that this works. And to show that it works, you use this magic square argument that I'm not going to describe, but you can look at my notes or. Yeah, and the thing is that for this argument to work, you need the noise to be somewhat small. I don't remember exactly, but it definitely doesn't work in this regime. So when you're like this, then this nice magic square argument, it doesn't work because there's too much noise. Then the only way we know how to prove this kind of statement is using Fourier analysis. If you want, you can take the Fourier analytic argument and, well, Fourier analysis is the same as Boolean function analysis, just a different thing. If you want, you can take this argument and you can do it without calling it Fourier analysis, and then you get a different argument, but it's still the same. Yes, so just recently I saw a talk in India where somebody proved it without using Fourier analysis, but otherwise it was exactly the same proof. Okay, so sometimes you can, yeah. Okay, so this linearity testing theorem is also known as BLR test, Bloom-Luby-Rakov. And this nice proof that I'm going to give to you is in some other paper, but and it has many, many authors. And one of them is Johan Hostad, and he supposedly is the one who came up with the proof. So this is recorded. I don't know if it's true, but well, even if not, it's a nice story. Okay, and now we will prove the theorem. Really, the proof is quite easy. So maybe it's not as nice as this magic square proof that I haven't described, but yeah, otherwise it's better. So I guess we can forgive it. Yeah, so this is a proof of linearity testing. Okay, so the first step, here we have something about probability, and I want to convert it into an expectation. Something about expectation. Okay, so suppose f from plus minus 1 to the n to plus minus 1 satisfies the probability of f of xy equals f of x of y is 1 minus epsilon. Okay, so you want to turn this into an expectation. Then the expectation of f of xy x of y, this is the probability that this mess is equal to 1 minus the probability that is equal to minus 1. Okay, so because we're multiplying plus minus 1 here, this is either 1 or minus 1. This should remind you of Gauer's norm. Yeah, the Gauer's norm is a product of 4 terms, and here we have only 3 terms. So if we had 4 terms, it would just be the U2 norm, I think. Okay, so the probability that this is equal to 1, this is 1 minus epsilon, and then probability that it's minus 1 is epsilon. So this is 1 minus 2 epsilon. And you should notice that if we have here like this, then we also would have this thing. And this is entirely reversible. So if you knew that the expectation is at least 1 minus 2 epsilon, then this is the same as saying that this probability is at least 1 minus epsilon. And we will need this in the end, at the end. Okay, so this we switch from a probability to expectation, but it's really the same thing. This gets more exciting when you work over a larger group, like if you work over 0, 1, 2, then you can't just do this, and you need to work a bit more, but here it's very easy. This is why we like Boolean functions, because it's either 1 or 0, or either 1 or minus 1. It's very simple. And now we're actually in good shape. So there's really only one thing to do now. And this is to substitute the Fourier expansion. And then we will simplify it and it will be done. Okay, so okay, so now we just substitute the Fourier expansion for each of the 3 copies of f. So this is going to be expectation of s f hat of s es of x over p of f hat of p p of y over u f hat of u u of xy. Okay, and now we're going to do a few steps at once. So we're going to turn all this triple sum into just a sum over st and u. So we're going to use the distributive law, and then we're going to use the linearity of expectation. Okay. Okay, so I just put all the sums together and I push the expectation inside. Okay, and now what we're going to do is we're going to observe that phi of xy is phi of x times phi of y. Okay, and then we're going to separate the expectation into the x part and the y part. Okay, so we wrote phi of xy is phi of x times phi of y. And then we just separated the expectations over x and y because x and y are independent. Okay, now what is this thing?
Delta is delta is
Switch with you.
Okay, so this is just the inner product of Ps and Pu. Okay, which is delta Su. So it's 1 if S is equal to U and 0 otherwise. And here is the same. Okay, so we can drop all the zeros. And what remains, the only summations that remain correspond to S has to be equal to U, and T also has to be equal to U. So really all of them have to be equal. Okay, so this is sum over S, f hat of S, Q. And this is the usual formula for the U2 norm. Yeah. Maybe the U2 norm is to the power 4, but it's the same kind of calculation. Okay, and now we're almost done. Okay, so this thing is, we're given that it's close to 1. On the other hand, so with here, we know that if you square the Fourier coefficients, then you get exactly 1. Okay, so if we square the Fourier coefficients, we would have got 1. And now that we cube them, then we also get roughly 1. Okay, so if we got exactly 1, if this sum of cubes were exactly 1, then the sum of the cubes were equal to the sum of the squares. So this is really possible, only possible if f hat of s cubed is equal to f hat of s squared for each s. So they need to be 0, 1. And now we can, because the sum of squares is 1, then exactly one of them is 1, and we get a Fourier character. Okay, and here we would like to say that, okay, the only way in which this is possible is that if one of them is close to 1 and the rest are close to 0. Okay, because when you cube, then you slightly decrease the thing compared to the square. And yeah, so this makes intuitive sense. And fortunately, it's also very easy to write formally. Okay, but if you've never seen this, then this may be a bit difficult. So I'll just show you how to do it. Let's make up some space. Okay, so we write this. Okay, now we replace f hat of s with the maximal Fourier coefficient. So this is at most sum of s f hat s squared times the maximum over t of f hat of t. Okay, and this makes sense because f hat of s squared is non-negative. Okay, but the sum of f hat s squared is, so this was written here. This is the expectation of f squared, and f squared is just 1. So the sum of f hat s squared is 1. So this is equal to 1. So this is just the maximum over t of f hat t. And we conclude that there exists t such that f hat t is at least 2m 1 minus 2 epsilon. Okay, but this is the inner product of expectation of f times t. And now you do this calculation here in reverse. And we conclude that probability that f is equal to t is at least 1 minus epsilon. Thanks. What? Okay, so this is stack calculation showed that this sum of cubes is very close to 1. And this is only possible if one of the Fourier coefficients is itself close to 1. And this is the same as saying that your the function agrees with this Fourier coefficient with probability close to 1. Okay, so this thing here is just, we wrote it above, but we use inner products, but otherwise it's the same. Yeah, so this is sort of a proof that writes itself. So the only non-trivial part was this inequality. Everything else is you just substitute the Fourier expansion and it just works out. And really this magic square argument is there's something a bit magical about it, like there's no reason for it to be true. So I haven't shown it to you, and there's time now, but I don't think I remember the details. Anyway, you can look it up. This is really just a big calculation. And maybe this is a good point. So this magic square argument, maybe it's a bit magical, but you can see what's going on. So you do this self-correction, and it turns out that this self-corrected function is the character that you're looking for. And here you do this calculation, and everything works out. And maybe here you kind of see what's going on. So when you're looking for this character, so you say, okay, let's take this arbitrary function f, and let's it's a mixture of characters. Okay, out of generality, because every function is a mixture of characters, and let's show that in this mixture, one of the characters is very prominent. Yeah, and you do the math, and it works out. But when we prove more advanced theorems, then okay, so I can follow the proof, but I don't understand it. Yeah, and like when I was given this class by Yuval Filmus, who proved many of these theorems, I bet he also doesn't understand it. So like we can come up with the proofs, but we don't see what's going on. Yes, it may be similar if you've ever seen these Hoffman-bound based proofs of intersection theorems, then you can follow the proof, but nobody knows why it works. Like it works, but when it doesn't work, we don't know why. Okay, so here I think some of the younger people, they have more intuition than me, but it's slightly mysterious. Yeah, but I think this proof is not so mysterious because it's very simple. Okay, so questions about this proof?
Yeah, I have a question about the smallest value of the lower bound of our property.
Yeah.
1 minus 1 over 2 plus delta the reason we choose this value is this expectation we need this positive.
Yeah, so kind of the reason is that if you take a random function, then you expect to get half. So if it's far from half, so here we took far from half positive, but you can also be far from half negative, and then we'll be close to a negative factor. Then the function is not pseudo-random in some way. So, and this will come up later, but there's this notion of pseudo-randomness that also it's commonplace in external combinatorics, where pseudo-random functions or quasi-random functions or whatever, so there are many possible definitions, they behave like random functions in certain senses. Okay, so here the pseudo-randomness notion is that that this equation probability goes to half. Okay, and really what this thing means is that if all of the Fourier characters are small, then the function behaves pseudo-randomly in terms of this linearity test. Okay, so if you've ever seen proofs of Roth's theorem, or stuff about three-term arithmetic progressions, it's the same idea. Okay, so it's exactly the same calculation. So this quantity here, it's not quite the same, but when you do arithmetic progressions, you get a similar result. Then there's this main term, which comes from the empty Fourier coefficients, and now it's in the error term. If all the error terms are small, then you can prove directly that they are arithmetic progressions because it behaves like the main term. And otherwise, the only reason why this cannot work is this because you have a large Fourier coefficient. And then you do it in Roth's proof at least, and you transcend, you go inside a subgroup. And you continue like this. So it's like the proof of the regularity in general, easier. Okay, so this is the pseudo-randomness point of view of this.
I have another question.
Yeah.
So for the linear testing, this one, we can't get some one proportion stability result.
Of what?
This one is 99 proportion stability.
Right.
So if you want to get something, this property is satisfied, it's at least epsilon. So the 1% stability.
Yeah, so I think that the 1% here is really the 51%. So you're really not saying anything if it's at least 1%, because a random function will satisfy it with probability close to a half. So for the 1% to make sense, then you need the field, the group to be not Z2, but some group which goes to infinity. And then it makes sense. So people also study linearity testing over arbitrary abelian and non-abelian groups, and then it doesn't make sense. This is maybe none of you are electrical engineers, but in electrical engineering, they also like Fourier analysis. But for them, the dimension is usually fixed, like 2 or 3 or 1 sometimes. But the group goes to infinity. Or sometimes it's infinite. Like if you do Fourier transform on the torus, then it's infinite. And here the group is Z2, but the dimension goes to infinity. So it's kind of the other limit. Yeah. Also, you can notice that in the statement, you don't see n. Okay, so n is the dimension of f, like the dimension of the domain of f. But in the statement, there is no n. So this statement is dimension free. And this is very important. Sometimes it's a lot easier to prove results in which n does show up, but these are weaker. So for example, here we're testing that f of xy is equal to f of x times f of y, but let's say that now we switch from plus minus 1 to the n to 0, 1 to the n. But we keep this equation. Okay, so now instead of product being XOR, then the product is now n, the n function. Okay, so then the functions which satisfy this with equality are the 0 function and the nth, which includes the 1 function. And you would like to say maybe that if you satisfy this with probability close to 1, then you have to be close to either 0 or an n function. Okay, so this actually comes up in social choice theory in an area called judgment aggregation. So this is one of their paradoxes. It's called the doctrinal paradox. So I won't describe it, but in some setting, the only kind of decision that makes sense. So usually you want to say that majority is a good social choice function, but you know from like Arrow's theorem with stuff like that maybe you've heard of, that majority vote doesn't always work. And in that setting of the doctrinal paradox, whatever that means, then the correct answer is an oligarchy, which is an n function. It's their term from an n function. Then you would like to say that if this condition holds approximately, then you're close to an oligarchy. So then this guy in social choice theory proved this kind of theorem for 0, 1 to the n, but his result involved an n, and you need to work a lot harder if you want to get a dimension-free result. Anyway, so what we're going to do now, unless you have any more questions.
So
Yes.
how tight is the lower bound in the theorem linearity testing?
Yeah, so it's tied up to a constant factor in epsilon. I assume that my guess is that it's tight even up to the constant factor, but yeah. So I imagine if you took a character, let's say the one character, and you modified an epsilon fraction, then you can show that this thing holds probability very close to 1 minus epsilon. This will show that it's tight.
Yeah.
And the idea is that if you XOR 3 Bernoulli epsilon, then like you need to do the calculation and probably it's tight.
Right, and if we take for example, larger finite group instead of D2, and so what kind of lower bound will we get in this?
Yeah, so this has been researched. I don't know on the top of my head. So if the group is fixed, then you get the same thing, maybe a different constant factor. And the way to do it is you, so now you have a function from your group to the end to the group, and you need to, instead of doing it directly to get to the expectation, then you need to look at the correlation with the characters of the group. And then it will be very similar. If you care about the dependence of the size of the group, then I think this is also known, maybe only recently. Then you need to do the same calculations, but you need to be more careful. Yeah, so if you're interested, then ask me later and I'll try to find it. Yeah. And you can also look at, like there's no reason that the input and the output have to come from the same group. So it's also been studied. Also, like sometimes people study what if it's a function from the reals to the end of the reals. Then you maybe want a different notion of. Okay, so I think this kind of version was also studied for the reals, like with plus. Maybe Yoshikawa and a friend. Or you can ask maybe it's equal, to, there are many versions. Yeah, any more questions? Okay, so what we're going to do now in the remaining time is I'm going to describe some background and then we're going to start the next topic. So we have more of a chance of actually making it to where I wanted to arrive. Yeah, so we'll start with the property testing perspective. Okay. So this originates, I think, in program testing, self-correction. We don't care about the motivation. Okay, so there was some motivation from programming at some point. But since then, people forgot about the motivation. Okay, this is very common in mathematics. So we have a black box function which takes in an input, a vector in the Boolean cube, plus minus 1 to the n, and output something in plus minus 1. And we want to test that this black box computes a linear function. Okay, and how do we want to test it? We want to query it at only a few places, and then we want to make a decision. Okay, and we want two properties to hold. So the first property, completeness, is that if the black box actually computes a linear function, then we always have to answer yes. It's known as perfect completeness. And then in the sumness, so we want to say that if we answer yes with high probability, then the function is close to linear. Okay, so because you're querying the function at only a few places, then you won't be able to tell whether it's actually linear or not. So the best that you can hope for is to say that it's that you will, if it's far from all linear functions, then you will discover it with some reasonable probability. This is the best that you can hope for in this black box world when you only make a few queries. Yeah, because you can imagine like maybe I make 10 queries, and let's say I took a linear function and I modified 1% of the inputs. So then with my 10 queries, I will just, the probability to see nothing, none of these entries which I changed is 90%. So there's no way that I will notice that the function is not linear. So the best that you can say is distinguish between the two cases. One is when the function is linear, and the other one is when it's far from all linear functions. Okay? So this is property testing for the property of being linear. And the test is you pick x and y at random, and you check whether f of xy is equal to f of x times f of y. Okay, so if f were linear, then the test will always succeed. And what this linearity testing shows is that if the test succeeds with probability close to 1, then the function is indeed close to some linear function. Okay, so this shows that you can test linearity using only a constant number of tests, 3 tests. And now this field of linearity testing, it's one of the sub-areas of complexity theory. So some people, that's all what they do. So in the same way that you can test linearity, you can test being a polynomial of degree d. Okay, so you just look at the Taylor's norm of the ud or ud plus 1, whatever. This will still work out. Some point people got very excited about monotonicity testing. So you have this function f, and you want to test whether the function is monotone. So this you cannot do with a constant number of tests. But the optimal number was found, and this involved some Boolean function analysis. So it's difficult, so that's why people got excited. Yeah, so this is something that people consider worthwhile doing. But perhaps a better explanation is application to hardness of approximation. Okay, so let's say I'm giving you a system of linear equations over F2. So the variables are, let's say, 0, 1, and it's a system of linear equations. And your goal is to find a solution which satisfies as many equations as possible, like an assignment to the variable which satisfies as many assignments as possible. Okay, so if the system is satisfiable, then it's very easy to find a satisfying assignment. Okay, this is just Gaussian elimination. But let's say that the system is 99% satisfiable, which means that there's some way, some truth assignment, which satisfies 99% of the linear equations. Okay, now let's say that there are n variables, so you can find the best assignment in time 2 to the n by just trying out all the different assignments. But in complexity theory, we're interested in polynomial time algorithms. So the algorithm should run in time, which is polynomial in n. Yeah, let's say that the number of equations is reasonable. And let's even say that each equation involves exactly 3 variables. Yeah, so it's like x1 plus x5 plus x7 equals 0. x2 plus x3 plus x4 equals 1. Something like that. Yeah, let's say that I promised you that there is some truth assignment that satisfies 99% of the equations. So how much can an efficient algorithm satisfy? Okay, so can you think of some algorithm which satisfies some non-trivial fraction of the linear equations? Any system. I'll give you a bunch of linear equations where the variables are 0, 1, and it's linear, so it's everything is an XOR. And you want to find an assignment for the variables which satisfies as many equations as possible. So how many can you satisfy? Yeah.
Like first idea is just doing a greedy algorithm.
Okay.
Like start by IC as any attributes one by one. Maybe at random if we have probabilities involved.
Okay, so let's say random. Let's say I chose the assignment at random. How many of the equations do I satisfy? If I choose the assignment at random. So what's the probability that I satisfy a single equation?
Oh.
Half, right? So this way, I can satisfy in expectation half of the assignments, half of the, sorry, of the equations. And using a greedy algorithm, but you need to be slightly careful, then you can de-randomize this. You can take this algorithm and turn it into a deterministic algorithm, which employs no guesses. So it will be like your greedy algorithm, but you'll have to be a bit more careful. I mean, I guess maybe for linear equations, you just do greedy. So when the turn of variable x5 comes, and you look at if there are any equations of the form x5 equals 1 or x5 equals 0, then you choose the majority. So you want to satisfy the majority. And otherwise, you just choose an arbitrary value, and you simplify the equations. So this is the greedy algorithm, and it also gives 1/2. And now you can ask, okay, let's say that I'm telling you that the system is 99% satisfiable. There's some assignment that satisfies 99% of the equation. Is there a polynomial time algorithm that satisfies 51% of the equations? Okay, so if you believe that P is different from NP, then the answer is no. Okay, so this is what's known as the hardest approximation result. So there's no polynomial time algorithm which can distinguish between systems which are at least 99% satisfiable and systems which are at most 51% satisfiable. This is true for any, like also 99.9 and 50.1% and whatever. Yeah, so the way that you do this is you have to use the PCP theorem, whatever that is, and parallel repetition, whatever that is, or maybe together. What it all boils down to in the end is this linearity testing. Okay, so the same thing here. The only difference is that instead of having one function, we have 3 different functions. So you have f, g, and h, which satisfy this equation, like with f, g, and h, the probability not close to 1, but close to 1/2. So this is the half plus delta regime. And somehow, so these functions, it's a bit hard to describe without describing anything else, but they kind of, you want to decode them to these characters, and you're able to decode them using this list decoding interpretation of the theorem. This is roughly the connection. Yeah, I won't describe it any further, but there is some connection, and like really what you need to do is this analysis. And this is how you prove this 51% versus 99%. Yeah.
So, especially because the theorem mentioned free, if it that although we cannot test whether f is linear or not in a constant dependence on epsilon, but we cannot construct chi of it.
So you are able to get access to PyOS, at least in the setting where, in the one-minus epsilon setting, when epsilon is smaller than some constant, using this self-correction. So what you do is so you want to know what f of x, what ps of x is. So you look at f of y, f of xy for a few values of y, and you take majority, and this will work. Yeah, if you wanted to do it this way, then it's probably covered in literature, but cannot remember ever seeing. But this is close to what's known as this recoverable codes, this correctable codes, this decodable code. They're like there's many different versions where this is what they want to do. Yeah, this is the coding theory point of view. Yeah, any more questions? Okay, so the last 10 minutes are going to be a preview for tomorrow. Tomorrow we're going to start the proof of the KKL theorem, and probably won't end it tomorrow because there's need to prove hyperconductivity, whatever that means. Yeah, but let's just describe the setting. So the setting is collective coin flipping. Okay, so all of us, we want to flip a coin. Okay, so all of us toss our own coins. And then we feed all of these coin tosses to some function which outputs, supposed to output a fair coin toss. And the assumption is that each of you tosses a fair coin. And the coins will be plus minus 1 value. Okay, now what kind of function would you use to aggregate all of these coin tosses to get a fair coin toss? What's the natural candidate? Okay, parity actually is an interesting idea. I think maybe the usual answer is majority. Like if people vote on some topic, yeah, okay. Let's say it's not coin flipping. Let's say we have to choose whether we're going to have Italian or Indian. And now we want to aggregate the results, and now maybe parity makes kind of strange sense, but the majority makes more sense. Then we also maybe want the function to be monotone. So if more people want Indian, then maybe we will choose Indian or something. Okay, now let's say that I really like Indian food, and I want to pay some of you to vote Indian. Okay, and I want everybody else is, let's say they're tossing a coin because they don't care, that they never had anything but Korean food or Chinese, whatever. And let's say I want to guarantee that with probability 90%, the answer would be Indian. So how many of you do I need to bribe? And let's say there are n of you. And we're doing this majority vote. Okay, so each of you flips a coin. Now we're back to this coin business. And I want the answer to be 1. So I'm willing to pay some fraction of you to switch to 1. And I want to guarantee that the output is 1 with probability 90%. If I want to guarantee it with probability 100%, I need to pay half of you. Okay, but this is too much. So I'm willing to pay fewer of you, and in return, instead of guaranteeing the answer is 1, it's just be 1 with probability 90%. So how many of you do I need to bribe? Let's say there are n of you.
Positive question.
Yes, so square root. So not positive, but square root n. And why square root n? Because roughly speaking, this is a central limit theorem. So if we sum all of your coin tosses, then we will get something which is plus minus square root n with, no, let's say with probability 0.9, it will be between some minus constant square root n and plus constant square root n. Okay, so in order to bias it past 0, it's enough for me to pay some square root n times some constant, where the constant depends on this 90%. Okay, now you can ask, is there anything better to do? So I'm looking for an unbiased function. So it's half of the inputs are 1, half of the inputs are -1, and let's say you also want to be monotone. And I want this square root n to be better. So is square root n the optimal thing that you can do, or maybe you can construct a function which is more resilient? So what do you think? You think square root n is optimal, or maybe there's something better that you can do? Yeah, so it's not clear, and I'm actually not sure what the KKL people thought the answer would be. So this would be somebody in lineal, because Nelson played lineal, remember? Yeah, so we actually don't know the optimal answer. So there is a function was constructed by Boolean and somebody, where you need to bribe n over log n squared people, okay, to bias the output. And definitely for any function whatsoever, you can always bribe n over log n people. Yeah, this is the KKL theorem. So in any such, it's not the usual formulation, but it follows. So for any monotone unbiased function that they give me, then it's possible for me to pay n over log n of you, and to drive you to vote 1, and afterwards the output will be biased towards 1 with a constant probability. Okay, so n over log n is the limit. We don't know how to achieve this limit. This KKL theorem is tied for the usual formulation, which is a bit different. So this KKL paper from 1988 is the first paper in Boolean function analysis, and it's the source of much of the terminology which comes from social choice theory. So the KKL theorem is about something called influence that I'm going to define tomorrow. We also talk about juntas in this area. So this also comes from this social choice background. This the proof of the KCalcium. We're going to see it uses something called hypercontractivity, which is something from either functional analysis or it's connected to log sublevel inequality, which is also something from functional analysis, but it also shows up in, I guess, the theory of convergence of Markov chains. So you could call it probability theory. This hyperconductivity, I haven't described what it is, but it's some kind of something that you can prove by induction, and then you never have to use induction again. So it's kind of an inductive argument which you prove once, and you can use it many other times. This is where all of these free analytic proofs that they become somewhat strange. Okay, so you can follow all this stuff, but maybe you cannot see what's going on. So you'll see it tomorrow.